Hi, this is the third Physics 2212 lab magnetic field of a bar magnet. Okay, so the purpose of this lab is to observe magnetic fields through a visual representation as well as the relationship between distance and magnetic field, and also to use the distance dependence of magnetic fields and the Biot-Savart law to find the magnetic moment of a bar magnet. Some key concepts we'll use for this lab are using a bar magnet to model a magnetic dipole, the Biot-Savart law, which is our 1 times 10 to the minus 7 constant times 2 mu over r cubed, a linearization formula we'll use a little later, and the distance dependence formula of a bar magnet. So a key assumption we made for this lab is we assumed that the bar magnet acted as a magnetic dipole in order to apply the Biot-Savart law in solving for mu. And just a preview of our results, mu had a value of 2.34 amperes times meter squared, and n had a value of minus 3.0168. And so this was our experiment. We defined the system as the bar magnet and the surroundings as everything else. The location of the magnetometer on the phone was found by sliding the phone perpendicular to the ruler, both vertically and horizontally, so that we could see at which position of the phone relative to the magnet the strongest magnetic field was being read. And once we found this location, we marked it with another piece of tape as shown here. So first we had to orient the phone so that the Earth's magnetic field didn't interfere with the magnetic field of the bar magnet. Then the on-axis distance from the bar magnet to the magnetometer was found using the ruler for several different magnetic field values. These values were linearized by taking the natural log of each side and then graphed. And so you can see that we used the linearization equation we introduced in the beginning here to plot the natural log of the x component of the magnetic field to the natural log of the distance r. And so in the second part of this experiment, we found the off-axis magnetic field of the bar magnet. We did so by finding the on-axis distance for the bar magnet to the phone so that the net magnetic field was 100 microteslas. Then we slid the phone in the vertical direction, the same distance, and recorded each component of the magnetic field at this location. The y component of the bar magnet was found by subtracting the Earth's contribution of the net magnetic field in this direction by the total B field. Some observations I made in this experiment are that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. Also, as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. This suggests that the distance shares an inversely proportional relationship to the magnetic field. Also, the position of the phone matters in terms of ensuring that the magnetic field of the Earth does not interfere with our readings of the magnetic field of the bar magnet. So the distance dependence equation generated by our Excel spreadsheet is y is equal to minus 3.0168x minus 14.575. And using the linearization equation we mentioned before, we can deduce that the value of n, this slope, is minus 3.0168, and the value of k, found by raising both sides of this ln of k is equal to minus 14.575 equation by E, is 4.67905 times 10 to the minus 7. We can then equate the Biot-Savart law to the distance dependence of the bar magnet to find mu, letting r equal 1 meter, and we ultimately found mu to equal 2.34 amperes times meters squared. And I was able to model the magnetic field of the bar magnet computationally. I first created a cylinder to represent the magnet at the origin and recorded my value of mu, then defining a function for the magnetic field at any point relative to the position of the magnet. I then created 6 observation locations, 2 of which being on axis to the bar magnet and 4 of which being perpendicular to the axis of the bar magnet. And at each of these locations, I created arrows representing the direction and magnitude of the magnetic field due to the bar magnet. So here you can see the 4 arrows representing the magnetic field perpendicular to the axis of the bar magnet. And then I was able to create an arrow representing the magnitude and direction of an arrow 45 degrees off axis by using the distance that I found experimentally as another observation location, and using my function for the magnetic field to calculate the magnetic field at this point. And here was the glow script model after I ran my code, and here were the values of the magnetic field at each location. The off-axis field, I found through the glow script model that the magnitude should be 2.81 times 10 to the minus 5 teslas. And for my experimental off-axis field, I got a value of 6.34 times 10 to the minus 5 teslas. And overall, between the theoretical off-axis field and the experimental off-axis field, there was a 126% change. So what we found in this experiment is that a bar magnet's magnetic field typically very closely models that of a magnetic dipole. So in this case, our choice of model likely yielded very accurate results. Some possible sources of error in this experiment are that the location of the magnetometer on the phone may not have been found very precisely, with a potential significant margin of error, skewing distance results from bar magnet to the magnetometer. Also, if the reading of the magnetometer did not match the Earth's magnetic field before the experiment began exactly, that may have skewed off-axis results of the bar magnet's magnetic field. So if I hadn't compensated for magnetic north, my results would have been much less accurate since the Earth's magnetic field would have interfered with my reading and skewed the results. I would have had to account for the Earth's magnetic field in some other way, like maybe subtracting it from the total magnetic field. And if I were to stick 2 identical magnets together and repeat the experiment, my measurements would have roughly doubled, as the magnetic field at a location relative to the 2 bar magnets would have also doubled. So to conclude, both the Biot-Savart law and distance dependence can be applied to bar magnets with accurate results. We found in this lab that bar magnets can be used to accurately model magnetic dipoles. And finally, that distance is an important factor to consider in determining the strength of a magnetic field. All right, that is all I have for today. Thank you for watching.